Hi, everyone. Thanks for your patience, as it's taken me a little longer to get these videos together because I've been having to do things a little bit differently than I had originally planned. Hopefully this one goes a little better than the last one. I'm trying not to totally reformat the slides because they're in a format that works really well for the Lightboard, which I hope to be back to on Wednesday. Um, but at the same time, that means I'm not recording things in Zoom exactly the way I've done in the past when I've recorded things in Zoom. So it's been a little bit of a learning curve. I think I figured out a situation here where you won't have to try and read writing behind me. Hopefully, you should be able to see me just sort of hidden away in the bottom corner here. So hopefully this will go a bit better than last time. So instead of starting limits in this next lecture, I was looking at the schedule. We're a bit ahead of where I thought we'd be at this point. So I actually wanted to slow down a bit and talk about something called compactness a bit. Um, and in particular, one important theorem called the Heine-Borel theorem that tells us something about these so-called compact sets, which we'll start by defining. Um, so before we can define what we mean by a compact set, we first need to define something called an open cover. So an open cover of a set K is a collection of open sets. So we're calling the collection of sets or the set of sets capital O. The sets that are in this collection of sets, we're going to call the O sub alphas. Those are the particular open sets that are in this larger set of open sets. So an open cover of a set K is a collection of open sets, capital O, such that K is contained in the union of all the O sub alphas. So sort of visually, you could think about you have some set K, maybe it looks like this, and you want to take open sets that cover this. And so maybe my open sets sort of maybe this is some sort of open set, and this is another open set, and this is another open set, and here's an open set, right? But I do this, so I don't have an open cover yet, right? Because if my O sub alphas are in yellow here, there are parts of my green set that are not covered up yet, right? But if I keep doing this, and right, these could overlap, like lots of things could happen. Right, so if I keep adding some more of these in, I'm just going to add some big ones in so that think we get it all. Okay, now we have the yellow sets form an open cover of this set K. What this theorem says is a set is compact, or sorry, sorry, I'm getting ahead of myself. This isn't a theorem yet. This is just the definition of an open cover. So this would form an open cover of the set K. Notice, and this is a little bit of a preview from where we're going, we could remove some of these. I could remove that one that was sitting right there, and actually I still have an open cover. So you could oftentimes you may have like too many things in your open cover, right? They're overlapping in a lot of ways. Um, and you could actually get rid of some of them, but in any event, they still form an open cover. Once you have an open cover, you can add more open sets and it would still be an open cover, right? So open covers are not unique. A set can have lots of open covers. But an open cover is just a way of sort of covering a set that may be open, may be closed, may be neither, with open sets. Now, sometimes you want an open cover because you want to be able to say something about a set while using properties of open sets, even though your set isn't open. So sometimes you want an open cover because then you can sort of pretend that sort of, well, in this little patch of K, my set is sort of like an open set because I've covered it with this open set. Um, so there are good reasons to do this, and in fact, we will make use of this idea that I might want to cover something with open sets later on. Now, that's all perfectly fine. Okay, so I can define open covers of things. Um, but what I want to do actually is add onto this now the definition of compact. So we say that a subset K of the real numbers is compact if and only if every open cover of K has a finite subcover. Okay, so notice there's no restriction in the definition of open cover that says that that has to be a finite set, right? You could have an infinite collection of open intervals. We'll look at an example in a second. Sorry, an infinite collection of open sets that form your open cover. We say that a subset K is compact if every time you have an open cover, it's actually a finite subcover. Okay, or you could take it, sorry, you could remove things until you get down to a finite subcover. So let's look at an example real quick. Just imagine uh, K being the interval, say 1, 3. Okay. And imagine that I want to imagine I have the open cover. So I'm going to take the collection of sets, capital O, which is going to be, now remember, capital O is a set of sets. Okay. So capital O is going to be the collection of sets x minus 1/2 to x plus 1/2. So these are open intervals where I'm taking an x in my set K. So basically what I'm doing is I'm creating an open cover. Let's say this is my interval 1 to 3. And what I'm doing is at every point in this set, so let's be clear. This maybe in yellow, right? This is the set K. And I'm now creating these little O sub alphas, which are essentially at every point, I'm going to create an interval with radius 1/2, right? And then there's one here, and I'm missing lots of them, right? At every point, I'm just creating a little interval of radius 1/2 around that point. So there are actually uncountably, infinitely many sets in this collection of open sets, right? Okay, so here's an open cover. This is an open cover of K because every element of K lives in at least one of these O sub alphas, right? Actually, everyone lives in more than one, but that doesn't matter, right? So I can show that, you know, if I take a K, say a little k in the set capital K, well, then in particular, K is in the interval K minus 1/2 to K plus 1/2, which is in this interval is in my set capital O. Okay, so I've shown an arbitrary element of K is covered by some subinterval in my collection O. So the set capital K must be a subset of the union of all the O sub alphas. Okay. All right. So I have a set, I have a open cover. Now, we don't know yet if this set is compact or not. Okay. If it is compact, then this open cover ought to have a finite subcover. Let's see if we could figure out a way to come up with a finite subcover. Well, you probably pretty quickly see, okay, if I sort of start here, one sort of somewhat naive way to do this, and not a way that'll always work. Sets can have very bizarre structure, but this is a nice interval, so maybe this shouldn't be too bad. Try to draw this a little more to scale too. So if I start at 1, and here's going to be 2 in the middle there. Okay, so I start at 1, and I'm going to take the open interval that's centered at 1 of this form. Okay, so what? That's going to go up to 3/2, right? And then I realize, oh, okay, so sort of 3/2 is the first point in K, or is the smallest point in K that isn't covered anymore. So let me go to 3/2, and I'm going to put my open interval there. Well, it's going to go like this, right? It's going to go from 1 to 2. Then at 2, I'm going to stick another open interval. Now, again, this is sort of a naive way to do this. There are more efficient ways to do this. So every time I go up basically to the end point of the last interval I added on, I add something there, and I keep going. Now notice I'm not done yet because I still haven't actually covered 3. So at 3, I'm going to have to put one of these sets. Okay. So what I do is I realize the union um, of the O sub alphas. So if I take this union, this in fact is actually equal to just the union of take uh, the interval 1/2 to 3/2, uh, 1 to 2, 3/2 to 5/2, union 2 to 3, union 5/2 to 7/2. Yeah. Now, it's not always the case that when you take your finite subcover, the union of those things is equal to the union of the open cover. Could be that the open cover was covering up a bunch of sort of empty space, or space that wasn't actually in your set. So you may not always get equality. In this case, you actually get equality, right? The important part here is not so much that these are equal, it's that we knew K originally was contained in this, but also now we have that K is contained in this union. Okay, and this is a finite cover. Okay, so from this open cover here that we built, we were able to pick out finitely many of them, in this case 5, that still covered the entire set. Now, notice that that actually is still not enough to prove this set is compact, right? I've shown here that just for a particular open cover, this particular open cover has a finite subcover. If I could do that for every open cover of this set, then I would be able to say for sure that it's compact. So you can start to see that it's sort of maybe a fool's errand, right? I mean, how would you ever possibly write down every open cover? So you're not ever going to sort of prove this by exhaustion, by just looking at all of the open covers and saying, "Oh, okay, great. All of them have a finite subcover, sure." Um, but at least this gives you an idea of sort of some of the mechanics for working with these things. All right. Now, some things to start to think about, right? We might want to know, what are the compact subsets of R? So you saw we did that closed interval 1 to 3, and you may have sort of picked up on the fact, and I guess we didn't prove it was compact, right? Um, but you know, you get the notion that maybe it is, okay? And so you notice that there was really nothing special about 1 and 3, right? So maybe any closed interval of the form AB would be compact, right? So by the time we're done, we'd like to have some idea of, what are the compact subsets of the real numbers. We might want to think about a bounded and non-compact subset of R. Um, to get this, you sort of think in the opposite direction. What about open intervals, right? If closed intervals were compact, maybe open intervals are not. Okay, now again, this things we've got to work on. Um, could we have a closed and non-compact subset of R? Is that something we have? So these are sort of questions I want us to keep in the back of our mind as we're going through the next theorems. Next theorem is going to give us an equivalent way of thinking about um, compact subsets of the real numbers. And so I think by the end of this, we'll definitely be able to come up with some of these examples. All right. So the theorem I want to talk about is something called the Heine-Borel theorem. So the Heine-Borel theorem tells us specifically for the real numbers, and it actually can be generalized to Euclidean space in n dimensions. So this is true in Rn as well. But a subset K of R is compact if and only if K is both closed and bounded. So what this theorem tells us is that the compact sets in R are precisely the ones that are closed and bounded. Okay. And again, this is if and only if. So if a set is not closed, it cannot be compact. If a set is not bounded, it cannot be compact, right? So in R or Rn, we're just as good to think about compact as meaning closed plus bounded. However, it is important to recognize that that is not the definition of compact, right? And that's important because in spaces that are not Rn, right, in function spaces, for example, so like this the set of all polynomials or the set of all continuous functions, this is not true anymore, right? So we have to be careful that this is not the definition of compact, but on Rn, or as was going to be important to us, just specifically on R, the compact sets are precisely the closed and bounded sets. Okay. Now, the goal of this video is going to be to prove this theorem. I think it's a really nice theorem to work through. It gives us an opportunity to get a little hands-on with the definition of compact, but also go back to some of those definitions that we saw last time about open versus closed versus accumulation point, like working with all those definitions and ideas again, I think it is really helpful. Um, Now, I want to say, so we're going to prove this. We're going to sort of do this in 3 steps. Okay. So notice that the first two, if I just sort of look at these first two together, this is really just proving the forward direction of this statement up here, right? So I'm going to show that if K is compact, then it has to be bounded. I'm going to show that if K is compact, then K complement is open. Saying K complement is open is the same as saying K is closed. That's one of our properties from last time. So if K is open, sorry, if K is closed, then K complement is open, and vice versa. If K is open, then K complement would be closed. So open closed switches under complements. So taken together, these give us that if K is compact, then K is closed and bounded. So the first two are proving the forward direction. The second one, or sorry, the third one is then really proving the reverse direction. We want to show if K is both closed and bounded, then K is compact. Now, in this case, right, the definition of compact is every open cover has a finite subcover. So what we're going to do is we're going to say if K is closed and bounded, and if I have an open cover O, then it has a finite subcover. Okay. So this is sort of going to be how I structure thinking about this proof. Now, the first two that prove the forward direction, and we'll see this as we do it, but I want to just sort of remark on it now. The forward direction of this theorem is actually true in any metric space. So it's not just true in Rn, it's actually true in any metric space that a compact set must be closed and bounded. However, in a general metric space, the converse is not true. It is not true in a general metric space that if a set is closed and bounded, that it must be compact. That's only true in special metric spaces, of which R is one such example. So we'll notice that in the proofs of 1 and 2, okay. We're going to prove them just for the case of being in R, but I'll sort of remark and show you that you really could do this in general metric space sort of notation. The last one, the last part of this, step 3, though, relies very heavily on the completeness of R. So this is something that proving the reverse direction is really something that's more special than just being in a metric. It requires something that's a little more special than just being in a general metric space. All right, so let's take these step by step. So first we want to show that if K is compact, then K has to be bounded. All right, so how are we going to do that? I'm going to take my compact set, okay, and I'm going to write down an open cover for it. So let O be the collection of all intervals of the form minus n such that n is a natural number. All right. So these are the intervals like -1 to 1, -2 to 2, -3 to 3, -4 to 4, -5 to 5, so on and so on and so on. Okay. Well, then if I take the union of all these, then the union, and here I'm indexing these over the natural numbers, So I'll call these like the O sub n's. You just get back all real numbers, right? That you're just taking the sequence of intervals that's growing larger and larger and larger. Eventually, every real number will be inside one of these intervals, right? So take any real number you want, no matter how large it is. Eventually, there'll be a natural number that's bigger than that in absolute value. The absolute value, natural number that's bigger than the absolute value of the given real number. And then that interval of the open cover will contain the real number you were interested in. Now I'm here assuming that K is a subset of R. Again, we could do this in a general metric space, but we're going to prove it for the case where K is a subset of R. So then K must certainly K is a subset of R, and so it must be a subset of this union. Okay. So what I've shown here is that this set of sets, as described, is an open cover of K. Excuse me. Now, K is compact. What does that mean? That means that open cover has a finite subcover. So since K is compact, there is a finite subcover of K. Okay. So that means you could actually cover K using only finitely many sets of this form. Okay. So what does that mean? That means that there's some largest interval that covers all of this. So there has to exist some natural number, I'm going to call it capital N, such that N is the largest natural number such that minus N to N is in the finite subcover. Okay, so again, you had every interval of the form minus N to N for every natural number. And now you have a finite subcover. So anytime now that you have a finite collection of these intervals, right? They might be something like you could have negative 10, 10, um, negative 5, 5, negative 101, 101, right? But there's only finitely many of these things that are remaining in your subcover. And what I'm saying to do is look at all of these values, choose the largest one. Okay. So that's what the capital N is. Well, then K, which is now going to be in the union of this finite subcover. So now I don't need N to be in all the natural numbers. It's going to be in some other set A, which is a finite subset of natural numbers. And that union, right? I'm taking the union of all these nested intervals. It's just going to be minus N to N. Okay. So what does that tell me? That tells me all my K values are between minus N and N. So the absolute value of K has to be less than or equal to N for all natural numbers, or sorry, for all K in my set, capital K. Okay. So this capital N is actually a bound. All right. So the idea here is if K is compact, you can take these sort of, I sort of think of these as just balls sort of centered at zero, right? And they're bigger and bigger and bigger and bigger. That forms an open cover eventually of all of R, okay? But then it's an open cover of K, okay? But now you've expanded this, and then you go, oh, well, it's compact. So there's some finite subcover. So now all of a sudden, the possibility of having these sort of infinitely sized things goes away, because somewhere in that collection of balls of different radius, you have some largest one now. Because with a finite set, there's a largest one. Okay. And so now that largest one must cover all of K because it's a finite subcover. So it still has to cover K, and that tells you the a bound on K. Right? All right. If you're working in a general metric space, the proof sort of follows a very similar notion, although you do need to define more carefully what boundedness means. When you're working in a metric space, you have to be a little more careful about what you actually mean by bounded, but you can essentially do something very similar here. All right. Uh, Now, in the second piece, we want to show that if K is compact, right? Our goal really is to show K is closed. The way we're going to do that is we're going to show that the complement of K is open. Okay. Now, this one, I'm going to draw some pictures as we go because I think the pictures are quite helpful to understanding what's going on here. Okay. Um, so we want to show our goal. We're going to assume K is compact. We want to show that the complement is open. So what does that mean? Well, if something's open, that means every point is an interior point. That means that at every point, I should be able to draw a neighborhood around that point that lies entirely within that set. So I'm going to take an arbitrary point, oops, in K complement. Okay. Excuse me. My goal is going to be to construct a neighborhood around this point that lies entirely inside K complement. Okay, so let's see how we're going to do that. Okay, so I'm going to define an open cover of K, not K complement, because I know K is compact. So I want to define an open cover of K to be, and this is going to look a little mysterious until I get all of this right written down. The neighborhood of radius delta x around x, check my notes, yeah, such that x is in K, where delta x is equal to the absolute value of x minus z over 2. All right, let's draw a picture over here to make a little sense of this. And in fact, I think it's actually helpful to draw this not just in the one-dimensional case, but I think actually in the higher dimensional case, this actually makes a little more sense. So imagine you have this set K, well, maybe K, I don't know. Maybe this is my set K here. And what I'm going to do is I'm trying to show K complement is open. Okay, so I have some point Z here. Okay, now I'm going to define an open cover of K. What I'm doing here is I'm looking at every point X that's sitting inside my set here. Blue is maybe not very easy to see. Let's try yellow. So at every point X, what I'm going to do is I'm going to draw a neighborhood around this point. And what I'm going to do is I'm going to make the radius of that neighborhood half of the distance between X and Z. So, sort of visually, you might look at this and go, okay, I'm going to do this. Okay. Then I'm going to come over here for some other X value. And I'm going to do the same thing, right? I'm going to put a neighborhood around this point of half the distance from X to Z. And over here, I'm going to do the same thing. There's a point in my set K. So I'm going to put a neighborhood of radius half the distance between that point and Z. And I'm going to do this at every point in this green set. Now, clearly, that's going to be an open cover of K because I have a neighborhood centered at every point in K. So every point is covered up by some value. Excuse me. All right. So clearly, O forms an open cover of K. And since K is compact, it has a finite subcover. Okay. So already you're seeing the idea of a lot of these proofs when you're assuming something is compact is you carefully build an open cover. You use the compactness to say there's a finite subcover, and then from there you draw sort of the conclusion you want. All right. So now this has a finite subcover. And now I'm going to let delta be equal to the minimum of all of the delta x so once you take your finite, and I should say in the finite subcover, okay, so you take your finite subcover, now look at all the delta x's for all the neighborhoods that are still remaining in your finite subcover. One of them is the smallest one. Okay. And what's important here is you have all these delta x's. Each of the delta x's up here is greater than 0. Okay. Z is not in your set, so these all have to be greater than 0. If you take the minimum of a finite set of things, all of which are greater than 0, that minimum will also be greater than 0. That only works if you're taking the minimum over a finite set. A finite set of positive things will have a positive minimum, but an infinite set of positive things could have a 0 minimum. Or, well, it may not have a minimum at all. It may have an infimum that's 0. So we have to be careful here. The finiteness here of the subcover is important. All right. So essentially what I'm doing is I'm looking for the smallest radius, like let's say here in this picture, right, of the three that I drew, right, this one, or this one sitting here has the smallest radius, and that's what I'm trying to pull out is which one of these has the smallest radius. Said another way, what this delta x is telling us is which of these open cover sets comes the closest to Z. That's really actually what I want to get at. Because now, like I know this one is the closest, and it only comes halfway to Z. So I can go around Z now, and I can put something of radius, of that same radius, and they're open sets. So even though it sort of looks like they're just touching up to each other, they're actually not intersecting because they're open at the boundary. Okay. Uh, so then if we look at the neighborhood of radius delta around Z, okay, a couple things. First of all, this lies entirely in, let me actually think about that for a second. Is that true? Uh, yes, sorry. This lies entirely in K complement, right? And the way you know that is that you know that these sets form a finite subcover, sorry, form a cover of K. It's a finite subcover, but it's still a cover of K. Um, So this set has to then be entirely in K complement. And now what you have is you've defined a neighborhood around Z that lies entirely within K complement. So what you've shown is that every point, so big picture, take an arbitrary point in K complement, there is some neighborhood that lies around that point that's entirely within K complement. That's the same thing as saying that Z is an interior point of K complement. Since Z is an interior point of K complement for any, I mean, it was an arbitrary choice of point in K complement, that must mean every point of K complement is an interior point, and hence K complement is open. Since K complement is open, K must be closed, which is what we really wanted. Okay. Again, this is relying very heavily on a lot of definitions and facts from the previous video. So you may want to go back and take a look at those. It maybe just your notes, like to just refresh yourself on some of those facts. But that's the idea. All right. So again, the idea is cleverly choose a cleverly choose an open cover so that when you choose a finite subcover, you can quickly recover the result you want. All right. Now let's take a look at the last part. So the last part says if K is closed and bounded, and if I have an open cover O, then K has to have a finite subcover. Basically, we're proving here the reverse direction. If K is closed and bounded, then it is compact. Okay. So let's take a look at this. Now, in this case, right, we're just starting with K closed and bounded. Okay. So I'm actually going to prove this by contradiction. So what I'm going to do is I'm going to start and I'm going to go since K is bounded, there exists some natural number n such that K is contained entirely inside this set minus n to n. And I'm going to give that a name. I'm going to call that set K1. Okay, so since my set is bounded, I know I can blow up some big interval, and this K will lie entirely inside that big interval. And I'm going to call that big interval I'm going to call that big interval minus n to n K1. All right. Um, Now, I'm going to assume towards contradiction that O is an open cover with no finite subcover. Now, what I'm going to do is I'm going to take this interval K1 and I am going to I'm going to basically think about cutting the interval in half. So I'm going to look at the interval from minus n to 0 and the interval from 0 to n. And the way I'm going to choose, I only want to take one of them. And the way I'm going to decide which one I'm going to take is I'm going to look and see whether sort of that left half or the right half does not have a finite subcover. One of them has to not have a finite subcover. The whole thing doesn't have a finite subcover. Therefore, when I break it up into halves, right, um, then one of those halves doesn't have a finite subcover. Okay. I'm going to break K1 into sort of, I'll just call these left and right halves. and choose the half on which K does not have a finite subcover. Okay. So again, I'm being a little hand wavy here because writing out the details I think obscures what's going on. But like you're breaking this interval in half, right? So you're going to say, okay, look at minus n to 0 and 0 to n. And really what you're doing then is you're intersecting them with K, and you're looking at at least one of those can't have a finite subcover. One of them, it may be that neither of them have a finite subcover, in which case you could take either one. But if they both had finite subcovers, right? So if both halves here had a finite subcover, then the whole thing would have a finite subcover. Because two, if you union those two finite subcovers together, you would get a finite subcover for all of K. But since we're assuming that it doesn't have a finite subcover, then one of the halves has got to have an infinite subcover. Okay. So take the half that has an infinite subcover. All right. Now we're gonna repeat this process. Uh, Repeat it infinitely, and we're going to define a sub k to be the left endpoint of k sub k, right? So you start with k1, you split it in half. You look at the half that has the infinite subcover, that's k2. Then you take that one, you take k2, you break it in half. You look at the half of that one that has the infinite subcover, call that k3. Keep going. So you're getting all these intervals, right? And what you want to do is keep track of the left endpoints and the right endpoints. So define AK to be the left endpoints of KK and BK to be the right endpoints. All right. Well, what happens then? Then the AKs and the BKs, those intervals are getting smaller every time. So AK and BK have to be converging to the same value. Call it K. They converge to a common value K. I'm gonna call that little k. Okay. Um, Now this is, you might wonder sort of, well, wait, how do we know exactly that's true? Well, really this is by completeness, right? So really what you're doing here is that you have all of these AKs are lower bounds for the set that you're converging to, and all the BKs are upper bounds. And so you have to have a greatest lower bound and a least upper bound, and that they're coming together. So that's what's going on there. So this is really using completeness. Um, and uh, so we need a contradiction, right? Because we're assuming towards contradiction. So our contradiction is going to be like, what is this thing K essentially, right? And the crux of this comes down to the following. Um, K has to be in the set capital K since capital K is closed. Right? A closed set contains all its accumulation points or limit points. So K, little k, has to be in capital K. But also, little k cannot be in capital K, if little k were in capital K, then I could cover up little k with something of some positive radius, and then I would be able to build a finite subcover of my set by taking the neighborhood around K and uh, and unioning it with some number of the K sub Ks, right, up to some point. So it must be that my little k is not in capital K. So this is, I'm just going to say here by construction. I will work on typing up a full sort of detailed, clear proof of this to explain it a little better. But fundamentally, what I want you to understand really is just and see are some of how you build these sorts of arguments. Um, and the contradiction you reach is that this K both is in capital K and not in capital K, which is a contradiction. Okay. And since we have a contradiction, it must be that this set O did have a finite subcover. So again, this argument actually is relying. It's we weren't sort of totally explicit about it in our writing, but uh, this sentence right here, the one I put in a box here, this is really using the completeness of the reals, and without that, this argument falls apart. If you go try to look up arguments online, you may see some that use some other theorems. You can use something from topology called Tikhonov's theorem. You can use the Bolzano-Weierstrass theorem. You can use other sorts of theorems to help you establish this. But what we're really trying to do here is outline a proof from, I don't want to say from first principles necessarily, but without invoking much more than just the completeness of the reals themselves. Now, in some ways, that's a fool's errand because of what I'm about to show you next. But let's just stop here for a second to note we've now proven the Heine-Borel theorem, right? Because we've now proved both directions. We've shown that if K is a subset of R, is closed and bounded, then it is compact. And we've shown that if it is compact, then it must be closed and bounded. Again, that only works in, we've proven it in R. It works more generally in Rn, but it does not work for every metric space. One direction does work for every metric space, the other doesn't. No, for certain kinds of bounded metric spaces, I should say. Now, we've seen, right, this Heine-Borel theorem is sort of intimately connected to the completeness. And it actually turns out that completeness actually gives you a fairly rich structure for the real numbers. So the following four properties of the real numbers are all logically equivalent to each other. So completeness, that every bounded set has a supremum, is logically equivalent to compactness, or sorry, to the Heine-Borel theorem, which is that closed and bounded sets are compact. Which is logically equivalent to bounded infinite sets having accumulation points. That's something we'll actually talk about more later formally as the Bolzano-Weierstrass theorem. And this is also logically equivalent to the monotone convergence theorem, that bounded monotone sequences converge. So what these equivalences really tell us is that there's sort of this rich mathematical structure, right? So all of these being logically equivalent means if one of them is true, all of them are true. The real numbers are in fact complete, so all of these hold. Um, and it really just sort of reveals that any one of these things, sort of as soon as you have it, it's enough to set off almost this chain reaction of structure, right? So you get just a little bit of structure, and now all of a sudden you actually have to have lots of other interesting type of structure to the real numbers. So we will stop there for this video. We will in the next video start uh, we'll start looking at limits more thoroughly. And also I will replace this video at some point with a more polished Lightboard recording. So if at some point you go back to watch this, it's possible that this recording is gone. It's just been replaced with a slightly nicer one, but I wanted to get this to you so you could keep progressing in the course.